Welcome to Fluid Mechanics N6. Today's presentation is going to be on flow in open channels. But before I begin, I do want to say that if you do not understand the relationship between angles and sides in a triangle, then this module will seem to be more difficult than it really is. But we will look at that sort of thing, and I will just expect you to know what will the relationship be between an angle and a particular side of a triangle. Okay, so if you struggle with that sort of thing, I will advise you to go and revise your maths course and make sure that you understand that. Let's begin. First of all, I am going to begin with a reminder of some of the things that you know already. The first thing I'm going to speak about is the hydraulic mean depth, also referred to as the hydraulic radius. We use the letter M to refer to that, and it is equal to the cross-sectional area of the flow divided by the wetted perimeter. What do I mean by that? Let's say you have a pipe, okay, and this is the cross-section of a pipe. And as you can see, the pipe is filled with water, okay? And so if this pipe has a diameter d, okay, finding the hydraulic mean depth will be finding, first of all, the cross-sectional area of the flow. And because the flow is completely filling the pipe, so the flow will have the same cross-sectional area as the pipe. And then you will divide that by the wetted perimeter. Now, the wetted perimeter is the perimeter of the cross section that is wet, okay, that comes in contact with water. And as you see here, this pipe is completely filled with water, so the entire perimeter of the circle of the cross section is wet. So the wetted perimeter will actually be the perimeter of this circle. And so if we go ahead and look for the module, it will be the cross-section area of the flow, which is just the cross-section of the pipe because the flow fully fills the pipe. It's going to be pi by 4d squared divided by the wetted perimeter. Now, the wetted perimeter, of course, is the perimeter of this circle of the cross-section. What is the perimeter of a circle? It's just pi multiplied by d. Okay, and so if you simplify, you end up finding that the hydraulic mean depth when you have a pipe that is having a flow that completely fills the pipe is actually equal to the diameter of the pipe divided by 4. Now, let's say you have a situation like this. Again, you have a pipe and we're looking at its cross section. The diameter of this pipe again is D, although I did not mention it in the drawing here. And as you can see, this time the water is not completely filling the pipe, okay? So only half of the pipe is filled with water. The other half is empty, okay? So the water is flowing in this pipe in such a way that it does not fill it completely. And so in this case, the cross-sectional area of the flow, as you can see, is not equal to the cross-sectional area of the pipe, but rather the flow, which is here, its cross-section is only half the cross-section of the pipe. And also, if you look at the wetted perimeter, the wetted perimeter in this case is not equal to the perimeter of the cross-section circle here, okay? It's not the perimeter of this circle, but rather the part of it that is wet, okay? And in this case, the wetted perimeter will just be half the perimeter of the circle because this is the part of the perimeter of the circle that is wet, okay? And so it's half the area, half the perimeter. And so if you do again cross-sectional area of the flow divided by wetted perimeter, cross-sectional area of the flow is half the cross-section of the pipe, okay? And then wetted perimeter is half the perimeter of the circle here, okay? And so you divide them and you will again end up with d over 4 as the hydraulic mean depth, okay? Now, this is just a coincidence that I've picked two examples where the hydraulic mean depth happens to be d over 4. It is not always equal to d over 4, okay? I just wanted to show you how we go about finding the hydraulic mean depth. The next thing we're going to talk about is Chesy formula. Okay. Now, Chesy formula is something that we introduced when we were presenting flow in pipes. So if you haven't watched that video, I will advise you to go and watch that video because I am just going to quickly run through the formula and I expect you to already know what that is. First, the flow rate, of course, the general formula for the flow rate is equal to the area multiplied by velocity. Now, in Chezy's formula, the flow rate is given as the area multiplied by Chezy's constant and then multiplied by the square root of the product of the hydraulic mean depth and the hydraulic gradient. Okay, so I is the hydraulic gradient. And so this is how you find the flow rate using Chezy's formula. And of course, because flow rate is equal to area multiplied by velocity, and you can see also in this formula, we have area multiplied by all this. So all this here must be velocity, okay? So therefore, in Chezy's formula, you can get the velocity using this equation here. And C again, as I said, is the Chezy constant. Okay, so now in most of the exam questions that you will get, Chezy's constant is going to be given to you. Okay, but in my opinion, in my estimation, 1 out of 5 exams that you do on fluid mechanics will have a situation where they will ask you to find C. And if that's the case, then this is the equation that they will present you with that you need to use in order to find C, okay? And so in this equation, of course, you already know what M is. M is the hydraulic mean depth. And so all you're gonna need to find is K. Now, what is this K that you have in the equation for C? It is a constant, okay? And this constant is dependent on the conditions of the channel that you are dealing with. So if you have a channel that has got smooth sides, okay, clean smooth sides, then K in this equation will be equal to 0.16. But if you have a situation where it's a channel with dirty sides, then K is going to be equal to 0.276. If it's a situation where it's a channel with sides that consist of earth, then of course the value of K is going to be equal to 1.23. Okay, so 1 out of 5 questions you get in your exam on this module will have a question where C is not given, but rather they will give you this equation, and somewhere in the question they will state the condition of the pipe, and that will tell you which value of K you need to use in this equation. And of course, M, that is just the hydraulic mean depth, which you will get using this equation here. Okay, I hope that is clear. Now, let us look at the hydraulic mean depth for open channels. Okay, let us look at the hydraulic mean depth for open channels. This is just a quick exercise we're going to do just to allow you to understand how we find the hydraulic mean depth for open channels. And so first, let us look at the situation like this. So this is a rectangular tank, okay, as you can see, and it's got its sides. B is the length and D is the height of the water. Okay, so we may call B the breadth of the water and D is the depth of the water, okay, inside of the tank. Okay, so how will you now do if you want to find the hydraulic mean depth? So first, you need to find the cross-sectional area of the flow because, of course, the hydraulic mean depth is equal to cross-sectional area of the flow divided by the wetted perimeter. So the cross-sectional area of this flow, since we know the breadth and the depth, we can just multiply the two together. That will give us the cross-sectional area of the flow. And then the next thing we need to find is the wetted perimeter. Now, the perimeter that is wet in this case, of course, is going to be this length plus that length and then plus this length. Okay, so that is the part of it that is wet. Many students make the mistake to also add the length here, but as you can see, this is an open channel. So the top part is open. So there is no material here. There is nothing here that gets wet. The water is pretty much exposed to the atmosphere. So the perimeter of the tank that gets wet is just this length here plus that length there and plus this length here. So the wetted perimeter therefore is going to be equal to D plus B plus D, okay? And so because we have D and D, so you can very well say 2D plus B, okay? So that will be the wetted perimeter. And so therefore, to find the hydraulic mean depth, all you need to do is to divide the cross-sectional area of the flow by the wetted perimeter, and that will give you this expression here, BD over 2D plus B. I hope that wasn't too difficult to understand, but just in case it was, let us look at another example. So now, this time you have again a tank, and in this case, the water that fills the tank has a square cross section. Okay, as you can see, the water filling the tank here has sides of C on its cross section. It's C everywhere. And so, how do we find the hydraulic mean depth for a situation like that? First, let us look at the cross sectional area of the flow. And if you do that, it's simply C times C, so it's C squared. Okay. The second thing we're going to need to do is to find the perimeter that is wet, the wetted perimeter. And in this case, it's going to be this length and plus that length. And if you look carefully, you will see it's C plus C plus C, so it's 3C. So the wetted perimeter is C plus C plus C, as I said, so 3C. Okay. So now to find the hydraulic mean depth, all we need to do is to divide the cross-sectional area by the wetted perimeter. So when you do that, you have C squared divided by 3C, and it's equal to C over 3. Okay, so that will be the hydraulic mean depth when you have an open channel with a flow of water that's got a square cross section. Let us look at another example. Now, in this case, we have a channel that is in form of a V, okay? And as you can see, the water, or is, let's say the angle here is 60 degrees, and that angle there is also 60 degrees. So of necessity, we know that in a triangle, the sum of angles is 180 degrees. So that angle there doesn't even need to be mentioned. We will know already from these two angles that that is also 60 degrees. And because you have 60 degrees everywhere, then you can say that the cross-sectional area of this flow is actually an equilateral triangle, okay? A triangle that has got sides that are equal and angles that are equal, okay? So this side of the water is A, that side of the cross-sectional area of the flow is also A, and this side also is A, okay? Now, when you have a situation like that and you have to find the hydraulic mean depth, of course, you're gonna need to find the cross-sectional area of the flow. And now, for you to be able to do that, remember for a triangle, if you want to find the area of a triangle, you need to do the half multiplied by the base and multiplied by the height. Okay, half the base multiplied by the height. Okay, that is how we find the area of a triangle. So in this case, I can say this is a triangle that has been inverted. Okay, so the top is down and the base is on top, but that shouldn't complicate calculations. So if I have to find the area, I may take this length here as my height. Okay, that length there. Okay, so this will be my height. Okay, this length will be my height, and this here will be my base. And then to find the cross-sectional area of this flow, then I will have to do half the base multiplied by the height. Okay, and so what is this height going to be? And that is why you will remember in the beginning of this presentation, I said I will expect your maths to be good when it comes to triangles and angles inside of a triangle and the sides of a triangle. Okay, so how will you find this side here for the height? Of course, this height is dividing the angle at the bottom in two. Okay, so you will have 30 degrees on this side and 30 degrees on this side, and therefore this side here should be equal to A multiplied by the cos of 30 degrees. Okay, this is just from mathematics. Okay, if you